Welcome back to another video, everybody. Today I want to continue talking about integrals. This time I want to talk about some of their rules and properties. Now, as we discussed in the last video, the integral of a function is known as the antiderivative. So if we have the integral, say, of f of x, and we let this be maybe capital F of x, this new function, then if we differentiate that f of x, we will return to the original f of x. So this is the relationship between derivatives and integrals. So that means that a lot of the rules that apply to derivatives are going to be very similar for integrals. Let's start with probably the easiest one, the power rule. Now, as we remember, if you take the derivative of x to the n, you'll get n times x to the n minus 1. That's the power rule for derivatives. Now, for integrals, we're going to have to do it the exact opposite way since it's the opposite function. What does that mean? Well, here we brought it to the front to multiply and then subtracted 1. So let's work backwards. The last thing we do is subtract 1. So the first thing we're going to have to do for this is actually add 1 and plus 1. Then, for a derivative, we brought the exponent down to multiply, so now we're going to have to bring the exponent down to divide. So the exponent comes down, and we get 1 over n plus 1. And so this is what the power rule looks like for an integral. The integral of x to the n is equal to 1 over n plus 1 times x to the n plus 1. This makes sense because what if we take the derivative of this? Remember, if we take the integral and then take the derivative, we should get the original thing. If we take the derivative of this expression, we'll bring this n plus 1 down, and that'll multiply by the 1 over n plus 1, and it'll just cancel. And then subtract 1 from the exponent, and you get x to the n, which is the original expression. The only other special case I want to talk about right now is for e to the x. Now, e to the x is very special because when you take the derivative, you get e to the x back. What that means is that taking the integral of e to the x also returns e to the x, because to go from here to here, you would need to differentiate e to the x to get back to e to the x. So this relationship holds as well. Now, those rules are true. However, I have been lying to you about something. Let's take that integral of e to the x again. This is not actually equal to e to the x, technically. It's equal to e to the x plus c. What? What's c? What is that doing here? C is what's known as the constant of integration. What does that mean? Well, right now, what we're looking at is an indefinite integral. When you say you want to find the area under the curve, typically, that'd be within some portion. However, the antiderivative is just a general function, as opposed to an exact number like this should give, right? Any area is going to be a finite number. Now, what does that mean for us? It means that every time you take an indefinite integral, it has to define whatever this could be. Now, the problem with that is that this curve, where the axes are here, looks pretty much the same from this x value to this x value if the curve is higher like this. From here to here, the area is basically the same plus this chunk. Now, what is this chunk? Well, it's going to be this width, which it doesn't really matter, and then this height, which is some exact shift by a set amount over the whole function. Now we'll call that c. Now, the reason why this width doesn't matter is because if you multiply any number by a random constant, you'll get a random constant back, just a different random constant. But we just use c to denote all of the random constants. This should actually also make sense in the context of an antiderivative being the exact opposite of a derivative. The indefinite integral is the antiderivative. If you take the derivative of this expression, you'll get e to the x by itself because when you differentiate any constant, you get 0. Now that means that, for example, the integral of cosine x is equal to sine x plus c. Now, we know that if you differentiate sine x, you get cosine x. And if you differentiate c, you get 0, which means that sine x and sine x plus 2 and sine x plus a billion are all valid expressions for the antiderivative of cosine x, just depending on what your initial conditions are. Now let's talk about a definite integral. A definite integral just looks like this. It's the same integrand sign, but we're going to have from point A to point B of some function. Now, what this measures is the amount of change from point A to point B of f of x, which means if it looks like this and the axes are here, from here to here, there is a certain amount of increase, and that's this much. But if it's here to here, then the same amount of increase is present. Now, what this means is that if you evaluate a definite integral, you actually don't need the plus c. And the reason for that is because of the fundamental theorem of calculus. The integral from a to b of f of x, again, using capital F of x to denote the antiderivative of the function, we're going to have f of, or capital F, rather, of b minus capital F of a. This is a very important expression. It's fundamental to calculus. Now, the antiderivative of b is always going to end in plus c, but so is the antiderivative of a, which means the plus c here and the plus c here are going to cancel out because of this minus in between them. So there's never a plus c to worry about in a definite integral. So I hope you're starting to learn the basics of integrals with me, and I hope you understand the difference between an indefinite integral and a definite integral. Thank you so much for watching.